kind of TR do you want to use? Correct. TE controls T2. In order to accentuate T2, what kind of a TE do we need?
A long one.
Correct. Always remember, T1, short TR, short TE. T2, long TR, long TE.
Okay.
Okay?
So short.
Long, long. And then when we meet in the middle for proton density, we want to eliminate both T1 and T2. So how do I eliminate T1?
Like a long T R and a short T.
Very good. Got it?
I know.
You nailed it. You did nail it. Okay. So if we're looking at our parameters in gradient echo, they're the same but shorter. So we're still going to use that short TR and short TE, but it's going to be a shorter TR and a shorter TE for a T1 weighted image, okay? When we look at our T2 star weighted image, it's still going to be a long TR and a long T. It's going to be longer than the T1 in gradient echo, but they're going to be really short. So it's kind of mind-boggling. I know when I used to have students and we'd be doing a gradient echo and they'd look at the TR and the TR was like 300 and they're like, whoa, that's, it's a T2 weighted image, Lori. We have to bring it, no, time out, we're in gradient echo. So don't let that confuse you. The biggest thing about parameters in gradient echo is going to be what? We already know that our TR and TE is still going to be shorter and shorter for T1, and our T2 star weighted is going to be long and long, even though they're shorter than what we're used to. What is going to be the biggest deciding factor? Flip angle. Go ahead, Sherry. Why? Why?
Because it doesn't need to be 90 degrees.
Okay, so if I want a T1 weighted image, how would I set my flip angle?
Between 30 and 70 degrees.
Let's stop, don't be giving me numbers. Let's make it a little simpler. You've already read ahead, haven't you? You've read the slides, right?
No.
You haven't? Oh, pretty good. Okay, so for a T1 weighted image, with our flip angle, we want to have a larger flip angle, okay? So let's look at this. In gradient echo, TR and flip angle affect T1 recovery. Using a short TR, still going to create that image with a T1 weighting, and it does not permit T2 and proton density weighting, okay? By using a variable flip angle, again, less of the NMV gets flipped over into the transverse plane. Therefore, T1 recovery happens quicker, right? TR can be drastically shortened, okay? Might be still writing? You got it? Okay, so remember, gradients cannot compensate for the T2 star or for the inhomogeneities. So the T2 weighting is referred to as T2 star weighting. Just as in spin echo, TE still controls the amount of T2 weighting or T2 star that has happened before we capture the image. These things will never change, okay? TR is always going to control our T1. TE is always going to control our T2 or T2 star in gradient echo. Okay, so we need to maximize T1 differences. How do we do that? We want to prevent full recovery of fat and water vectors, so the flip angle needs to be large. Okay, so your flip angles in a gradient echo to get a T1 weighted image are going to be usually, again, it's not going to be 90. It'll be larger, like, let's say 45 to 65, somewhere around there. Okay? So flip angle should be large. Your TR, again, very short. You need to minimize your T2 star differences in order to, this is just the same as spin echo, guys. okay? But remember, in gradient echo, T2 weighting is referred to as T2 star decay, okay? Or T2 star. So if we want to minimize the T2 star differences, again, we still need to use that short TE. So T1 weighting in gradient echo uses still a short TR and a short TE, but a large flip angle. Less than 90, but large, okay? So on the opposite end here, when we're talking about T2 star weighting, how do we do that? We need to maximize T2 star differences. The long TE will maximize, will allow fat and water vectors to decay, and it will maximize your T2 star differences. We need to minimize T1 differences. How do we do that? Smaller flip angle. Okay, so gradient echo, T1 weighting, still a short TR and a short TE, but a large flip angle. Gradient echo, T2 star decay, long TR, long TE, but a short flip angle. So again, we're not going to be looking at TRs of 3,000, okay? Because the entire NMB does not get flipped over, and we're using a shorter flip angle, smaller flip angle I should say, a significant decrease in our TR and our TE. Okay, I'm going to show you some basic parameters. Okay, so proton density, same thing. Only we're going to stick with that short, small flip angle. So, long TR, short TE, large flip angle. Okay? TR is relatively long, it allows T1 recovery. Flip angle, small flip angle. I'm so sorry. Long TR to minimize T1, right? For proton density. Short TE to minimize T2, and then a small flip angle. Think of it just the same as spin echo, only all of our parameters are smaller, okay? T1, short TR, short TE, large flip angle. Proton density, long TR, short TE, small flip angle. T2 weighting, long TR, long TE, small flip angle. Okay, just that our numbers are, here's a significant decrease in our TR, excuse me, in our TE. So a long TR is anything over 100 milliseconds. We're used to 3,000, right? And you guys are just looking at regular T2 weighted. A short TR is less than 50 milliseconds. Your long TEs are between 15 and 25 milliseconds. A short TE is between 5 and 10. The low flip angle between 5 and 20. Change this from 70 to 110, because it really should be from 45 to 65. I need to go back in there and change that. We used to use the larger flip angles over 90, but they're not really that useful anymore, okay? So change that 70 to 110 to like 45 to 65. Okay, so gradient echo uses what to flip the spins? A gradient. What does it use? Gradient echo uses what to rephase the spins? A gradient. How does it apply the gradient? Opposite polarity. That too, right? That'll work. Okay, so gradient gets used to flip the spins. What is our flip angle on a gradient? Variable or less than 90, correct. Just by saying that, that tells us what? We're using less than 90-degree flip angle, lower signal, shorter time. Less of the NMD getting flipped over into the transverse plane, resulting in lower signal, correct. We take a gradient of opposite polarity. What does that mean?
Fast spins and the slow gradient and the slow spins with the faster one.
Correct. So if this is the slow end and this is the fast end, the next gradient of opposite polarity, it will speed up the slow spins and slow down the fast spins. Okay? What are the big differences between spin echo and gradient echo? Give me one, Mike.
Spin up uses 180 degree.
Give me another one.
I'm gonna say the parent,
The parameters, it changes the parameters. Give me another one.
A gradient echo plus a gradient
Or opposite polarity, correct. Compared, what's that? Abby?
The flip angle?
The flip angle, tell me about the flip angle.
Well, it's never going to be anything over 90.
Let's just say variable, a variable flip angle, okay? Because typically we're used to using a 90-degree for a spin echo, so we're gonna say variable, so we're not putting a number on it. We're gonna say variable, typically less than 90. Our parameters, what parameters affect T1 and T2 weighting? Is that it?
And the flip angle.
Flip angle. Okay, so now in gradient echo, in spin echo, it's TR and TE that affect our image weighting, correct? Now in gradient echo, not only do TR and TE affect our image weighting, but now the flip angle comes into play. So if I wanted to produce a T1 weighted image, I'm going to use, what, Santana? Am I going to use for, if I want in gradient echo, I want to produce a T1 weighted image. Tell me about my TR, my TE, and my flip angle.
For T1?
For T1 in gradient echo. Does that help?
Short
Short, still, we're gonna still use a short TR and a short TE,
Large.
but a larger flip angle. Less than 90, but larger than what we would use for a T2. What is T2 called, T2 weighting called in gradient echo? T2 star. If I want to create a T2 star weighted image gradient echo, my parameters are and a small flip angle. Good. Now when we say long TR and a long TE, our long TRs are over 100 and our long TE is 15 to 25, okay? Again, completely different than what we're used to seeing in spin echo, correct? The reason our TRs and TEs are so short is why? It's short, yes, it does shorten the time. That is another difference between spin echo and gradient echo.
Because the NMB
The,
is now
correct, the entire
all the way
NMD does not get flipped over
to the
into the
transverse.
transverse plane, so we don't need those longer TRs and those longer TEs, because only part of the NMD gets flipped over. Does that make sense? Questions? Where we are right now. Jamal, are you good?
I'm gonna, I came in late, so I'm just gonna have to kind of just read the slides over.
Okay, we're reviewing. Let's review it. spin echo uses. All right, I'll talk, let me talk. Spin echo pulse sequence uses 90-degree RF excitation pulse to flip the spins into the transverse plane, followed by a 180 rephasing pulse to rephase the spins to clean up any magnetic inhomogeneities, the magnetic susceptibility, okay, artifact, sweeps them right past the transverse plane so that they do not contribute to the image. A much cleaner image. Gradient echo. Gradient echo uses gradient to flip the spins into the transverse plane, but not at a 90-degree flip angle. Were you here when I said that 90-degree excitation pulse? We can now start saying flip angle. That is,
Okay, so that's the same thing.
that's the same thing. It's 90-degree RF excitation pulse that flips the spins over. We can call it a flip angle because it flips, right? In gradient echo, we don't use a 90 degree. We use less than 90, okay, to flip the spins into the transverse plane.
So it doesn't flip all the way.
Correct. So not all of the spins make it into the transverse plane. Okay? So when we go to rephase the spins, we use a gradient. A gradient cannot compensate for the T2 star decay or the inhomogeneities, the magnetic susceptibility, because it's just coming down on the spins. It doesn't push them past the transverse plane. Okay, so now we have T2 star decay contributing to the image. Make sense?
Why would we use gradient echo?
We use, good question. Does anybody know why we use a gradient echo? When do we use gradient echo?
Shorter time for the patient.
It is a shorter time. We use,
If the
Pardon?
patient can stay still.
not always, not always. Gradient echo is good to show blood flow. So you'll see gradient echo used in MRA. Okay? You'll see gradient echo used, how many of you guys scanning, observing, like really observing and seeing things? Okay. When we scan an MRI of the brain, we use a gradient echo pulse sequence. Does anybody else notice that?
Just showing the propeller, the flare.
Look at your brain, the brain protocol, especially trauma brain protocol. Okay, so we've talked about gyromagnetic ratio, correct? We've talked about mass number. Why is mass number important? Mass number of an element.
Determines the polarity.
How many protons are there?
Right, why is that mass number important?
Because it determines whether it's gonna be of an electron free or it's gonna determine the polarity of the.
It determines if
Anything with an odd mass number is MR active, okay?
Oh, yeah.
Yeah, don't forget what we've already learned now, guys. So anything with an odd mass number is considered MR active. What does that mean to us? That means that we can use it. Very good. We can use it. How do we use it?
with the line of frequency of that particular.
Very good. Okay, so even if we're not using, like, we're always going to use hydrogen. We're always going to send in an excitation pulse delivered at the Larmor frequency of hydrogen. Always. But if something has an odd mass number, it can contribute to the image. Okay? Metallic artifact, our magnetic susceptibilities, right? Our inhomogeneities, blood. Okay? Patients that have had trauma to their head, anywhere even, can develop a bleed. So let's stick to the brain for the moment, okay? Let's say the patient falls and hits their head. They can have a bleed in their brain. So with MR, that blood from hemoglobin is actually a inhomogeneity. It's one of those stragglers, okay? So that when we send in that 180 rephasing pulse, if there's anything in there from that's blood, bleeding, that 180 is going to clean it up. With a gradient echo cannot compensate for the inhomogeneities or the magnetic susceptibility.
But there are times you don't want to get it cleaned
Exactly.
up. So lose the iron and
Exactly. So for a brain trauma protocol, you would run a gradient echo, like T2 star weighted gradient echo. It's 2 minutes and 10 seconds long. We run it on all of our patients. Just like a diffusion is 40 seconds, we run that on all of our patients. Even if they came in and they have no history of stroke, it's 40 seconds. It's crazy not to run. What's that? Exactly. So our brain protocol consists of a sagittal T1, diffusion, T2 star gradient echo, T2 flare, regular T2, and an axial T1. You think, my God, you're going to be here forever. I said axial T1. You don't do axial T1?
No, we do axial
Yeah.
also. We do a hemo also.
Yes. Depending on the site that you're at is going to determine, But I mean, T1, T2, axials, your flare axials are standard, just about anywhere you go, and diffusion are standard, and your sagittal T1. Coronals we always do them post. The only time we would do them is if a patient has history of seizure, which we're going to get into all that in the second half of this course. We'll talk more about indications and which pulse sequences to use when. But this is all extra stuff for you guys. This is not on the test, okay? I'm just answering Jamarli's question, which is a very good question, and I want you guys to always be thinking. You guys see something in clinic and you don't understand it, and it's not where we are yet, it's in the future of where we're going, ask it anyway. I'm happy to explain it. Okay, so Jamarli asked, why would you do a gradient echo? Well, we always use gradient echo in MRA work, and we'll use gradient echo looking for blood, looking for bleed, because we don't want to clean up that extra signal that's given off by blood, okay, by the iron in the blood, okay? T2 flare. Why do we do flare sequences? A fluid attenuated. We use that for patients that have a history of MS, okay? Even if we do it routinely on all of our patients, and it's very useful for the radiologist, because if the radiologist does see some MS plaques in there, then they bring them back and we do a full MS protocol. Sometimes, if I see it, if I see some plaques in there, I'll go ahead and just run a sagittal T2 flare. Okay, but every site is going to have a varied protocol. You're not going to use exactly what we use at our site, okay? It all depends on the radiologist. It all depends on the patient's history a lot of times. When would we not use a gradient echo?
Hardware joint placements.
Exactly, any type of metal. Because the magnetic susceptibility and the magnetic inhomogeneity that's created by ferrous material cannot be compensated for or cleaned up by the gradient used in a gradient echo for rephasing. Okay, so the preferred sequence to do, whether it's a T1 or a T2 or a proton density, it doesn't matter the weighting. What type of pulse sequence would we do? A fast spin echo, which is a 90-degree excitation followed by multiple 180s. The multiple 180s, the more 180s you send in there, the more crap gets cleaned up. Okay, so in the spin echo pulse sequence, yes,
I have a question.
sure.
So for the proton density gradient, is that flip angle, the small flip angle, the same for the regular gradient echo flip angle?
For a T2. So if you want to get a T1 weighted gradient echo pulse sequence, you're going to use short TR, short TE, and a large flip angle.
Which is the 45 to 65.
Correct. If you want to get a proton density weighted, you're going to use the long TR,
Short.
short TE, and a small flip angle.
And is that the same range
The
or
low,
no?
the low flip angle, yes, the 5 to 20.
Okay.
Again, there are a lot, everything is a lot shorter, a lot lower in gradient echo. That's where we compensate, where that timing thing comes, their gradient echoes are so much shorter than a regular spin echo. Okay, so spin echo, T1, short TR, short TE, proton density, long TR, short TE, T2, long TR, long TE, gradient echo, T1, short TR, short TE, large flip angle, proton density, long TR, short TE, small flip angle, T2 star weighted, long TR, long TE, small flip angle.
Which is also
Correct.
same.
These are the gradient echo parameters when you're looking at TRs and TEs and flip angles.
Okay.
Okay, they're much, much shorter. Because remember, in a spin echo, what is our flip angle? 90. Now for a T2 or a proton density, it's 5 to 20. Okay, so it's significantly, everything is significantly shorter and smaller. Make sense?
Mhm.
Okay, so gradient echo uses variable flip angle and uses a gradient to flip the spins into the transverse plane. Uses a gradient of opposite polarity to rephase the spins. That gradient cannot compensate for the magnetic susceptibility or the magnetic inhomogeneity. Okay? Gradient echo, much shorter scan times, less signal. Okay? Not good for patients that have any type of metal. Okay, typically on a C-spine, we'll do sagittal T1, sagittal T2, and a sagittal stir. Gradient echo, axial, and T1 axials. If the patient has any history of metal or they've had a fusion in there, I'm not going to do a gradient echo, right? I'm just going to use a T2 fast spin echo. Because remember, what's that?
It makes sense now.
So you've seen it?
I've seen it.
Okay, good. Has anybody else seen it?
Yeah.
Typically, we'll use a
Side
gradient
by side.
echo. If the patient has had surgery, has had a fusion, we go to the T2 fast spin echo to clean up. Yeah. Make sense? Questions? So we are going to meet here next week. Exam will be here in class. Oh, question. How many of you have little ones for Halloween? Raise both of your hands. Teresa, raise both of your hands. It was presented to me to please have, to have Halloween off.
Yes.
We
I like it.
I take pride. Mike, you know what we can do? I just thought about this. Next week, after the exam, we'll go over that PowerPoint on magnets.
Okay, that works.
I was gonna do it like as a home assignment, to go over the PowerPoint that's, talks about the different types of magnets, resistive, permanent, superconductive. But instead, after class, because it's not something that's gonna blow your mind, it's kind of basic. After the test is over, we'll do that PowerPoint, and then we'll take the following week off, because the following week was when I was gonna do that. The test is next week. So we'll meet here next week, take the test. After the test, we'll do that PowerPoint on magnet, and then Halloween, I'll let you guys have it
Thank
all.
you. That's much appreciated.
Good?
Mhm.
Are you sure you wanna give us a test?
I'm positive. Because there's not much more I can tell you about image weighting, do you want to teach you in proton density, and spin echo and gradient echo. I think I beat it pretty hard.
Still 50 questions?
50, yes.
What chapter is that?
I don't go by books. I don't buy books.
I
Two
know,
of five.
I think my head's talking.
But my PowerPoint gonna be.
I do. So I'm willing to be cold, but.
2 and 5.
I thought it was 3 and 5.
Chapters 1 and 2 in the book, and,
Oh, there's 2.
and,
Image
I'm
weighting.
sorry, just 2 in the book, because we already did one. 6 and 7 on the, I think they're 6 and 7 on, they might be different than, this is my flash drive, so. It is 6 and 7, okay. And then after the test, we'll do these types of magnets.
So 2, 6, and 7?
Chapter 2, yes, chapter 2, PowerPoints 6 and 7. It's image weighting and full sequences. And again, we've only done 2 full sequences, and we've only done image weighting for 3 types of image weighting. T1, proton density, T2, spin echo, gradient echo. I think you guys pretty,
So doesn't 5?
5 has some of the changes in it.
2 in the book.
Chapter
it's
5
chapter
is a
2 in the
sequence.
book, and it's 6 and 7 PowerPoint.
Well, chapter 5 covers a little bit of the
Pulse sequences.
the pulse sequences.
In the book, okay.
Yeah.
Not in the way that I,
Here, yeah, chapter 5 page.
no, you don't wanna go to 5 yet, hang on.
Because chapter 5 has the parameters in it.
Yeah, it shows not the whole